Okay, in this video I'd like to finish up the algebra part of our algebra and trig review. So let's do that now. Problem 10, we have the functions f and g, and we're going to compute the composite function f composed g of x, and then state the domain of the composite function. We're going to do a lot of things with composite functions along the way. You'll see that. So f composed g of x just simply means that you're going to plug g into f. Whatever function is written after the open circle, you're going to plug that into the one that's before the open circle. Okay, so g is going to go into f, not the other way around, where f goes into g. Now g of x is 2 over x, so everywhere that I see an x in f, there's only one, I need to replace that with 2 over x. And so I've done that, replaced x with 2 over x, and now I would have to simplify. 1 is the same as x over x, so I can get my common denominator here of x, and then add the numerators. It'd be 2 minus x. 3, that's the same as 3 over 1, and since I'm dividing by a fraction, I would flip the denominator and multiply. 3 over 1 times x over 2 minus x would be 3x over 2 minus x. Okay, and that'd be as simplified as I can get it. Now, if we state the domain of the composite function, the first thing that we would want to know is the domain of g, because g is being inserted into f. Okay, so I got to know the condition on g before I plug these numbers into f composed g. Well, here's g of x. Okay, I know I can't divide by 0. X is in the denominator, so just don't let x be 0 for g. Now, I've computed the composite function and I've simplified, and 2 would be a problem with what I have circled here, right? Because I know I can't divide by 0. So all in all, I'm going to throw away 0 as a result of what I said about g, and then 2 from what I got here in computing the composite function. Okay, problem 11. A farmer with 1,300 yards of fencing wants to enclose a rectangular plot that borders on a river. He's not going to fence along the side of the river. He's just going to use the river as enclosure. Suppose that x represents the length of each of the 2 parallel pieces of fencing, and then y represents the length of the remaining piece of fencing. There's a picture given. What is the maximum area that can be enclosed? All right, so we're going to do some problems later on where we're going to be maximizing or minimizing a function. Now, there is a lot more to know about that, okay, but this is a great problem that you'll actually see again later on, okay. Now, the first thing that I want to do is I want to create a function that represents the area of this rectangle. Area of a rectangle is length times width. Right, so I'm going to start off by calling this area a function of x, and length times width at x times y. Now here's the thing. I don't want x and y floating around. I'd like to have only x since I've got a function of x. Well, the farmer only has 1,300 yards of fencing to work with. Okay, so if you take x plus y, that would be 1,300, or 2x plus y would give you, how much fencing he has to work with. If you subtract 2x from both sides, then y would be equal to negative 2x plus 1,300. That would be this remaining piece in terms of x. So where I see y in this function that I'm building, I can replace that with something in terms of x. That way everything is in terms of x. Distribute x, and so a of x would be negative 2x squared plus 1,300x. Okay, now that would be the function that models this situation. What is the maximum area that can be enclosed? Well, the thing to see here is that this function would be a parabola. Okay, I'm in a quadratic form, ax squared plus bx plus c. C would be 0. That's fine. A, b, and c can be any numbers, just don't let a be 0. Okay. So I do have a quadratic. Now the negative in front of the squared term would mean that the parabola would be opening down. Okay. I want to maximize the area, means I want to maximize the graph So I'd want to find the max point on this graph. The vertex would be the highest point on the graph, right? If I've got a parabola that opens down, the vertex would be the highest point. Here's the formula that allows us to calculate the vertex of this parabola. For this problem, little a is -2 and little b is 1300. So I'd want the opposite of b, that's -1300 divided by 2a. 2 times -2 would be -4. Okay, and then I'm going to want a of -1300 over -4 to get the y coordinate there. -1300 over -4 would be 325. And if I were to plug 325 into the function where I see x, I was getting 211,250. Okay, so the maximum area that can be enclosed would be 211,250 square yards. They're not asking for it, but if they wanted to know the dimensions of this rectangle, we could very easily get that. X has to be 325 yards, and Y would have to be, let's see, -2 times 325 is -650 plus 1300, that would be 650. Okay, so x is 325, y would be 650. So kind of how I drew this here, with y being twice x, would be the rectangle that produces the biggest area. Now, if the farmer went with any other dimensions, the rectangle wouldn't be as big as it could have been. Okay, he'd get an area that would be something less than what we see here. Okay, we're going to do more with maximizing and minimizing functions later on, but of course, here's an algebra example of that. Okay, problem 12 is the last algebra-related problem that we'll look at before we turn to trig. We're going to graph the function f of x by following the steps below. F of x is a rational function. We're going to be doing lots and lots of things with rational functions all throughout the course. Okay, and I'm going to mix in the things that we should already know about algebra, when we get to those spots. But let's take a look at graphing this by using the following steps. Part A, we're going to write the equations of the vertical asymptotes for f. The vertical asymptotes are going to come from any numbers that are going to be thrown away as a result of the domain. Okay, now when I look at f of x, I know I can't divide by 0. So 2 and -2 would be a problem, right? I'd want to throw those numbers away in the domain. Now because x cannot be 2 or not be -2, x equal 2 and x equal -2 would be the equations of the vertical asymptotes. Whenever you're asked to identify the equation of an asymptote, be sure that you write it as an equation. Okay, I'll have like my algebra students sometimes write just like 2 or -2. Don't do that. Okay, when you just write 2, that's vague and can be misleading. Okay, because somebody can look at this and think, oh, y equal 2 is a boundary, when in fact it's not. Okay. So be sure that you write the equation down, x equals whatever number it is, y equals whatever number it is. Okay, that's how WebAssign will want it also, by the way. Part B, divide completely. Okay, then we're going to write the equation of the horizontal asymptote for f. So I've got my division set up here. The expression that's in the denominator is going to go outside the division bar. The expression in the numerator is going to go underneath the division bar. That's always going to be the setup that you'll want. And we're going to begin dividing. So I'd want to think of a number such that when I multiply by x squared minus 4, the leading term is an x squared. Well, 1 times x squared minus 4 would be x squared minus 4. And I would need to subtract these expressions. X squared minus x squared is 0. -1 plus 4 is 3. You're subtracting the whole thing, so I'd want to look at it as -1 plus 4 is 3. 3 is my remainder. Okay, now the complete leftover information would be a fraction that I'd be adding to the quotient. The quotient is 1. That fraction would be 3 over x squared minus 4. And in general, you're always going to take the remainder over the expression that is outside the division bar. Also, when you divide completely, make sure that you have a plus sign here. Okay, some of my algebra students don't write that down, and when you don't write that down, it looks like you're multiplying, which of course we're not multiplying, we're adding. Okay, so it looks misleading there if you don't have that. Now, to get the equation of the asymptote, you're going to disregard this leftover and write down y equal whatever information you see to the left, which for us is y equal 1. Okay. Part C, determine the points, if any, where the graph of f will intersect the horizontal asymptote. Now, an asymptote is a boundary that the graph approaches, but it will never get there. That's actually not completely true. Okay. A graph can sometimes cross an asymptote. We're going to see several times where that happens once we get into the graphing part of the class, and we're going to go heavy graphing once we get into chapter 3 and 4. Okay, you'll see that. So a graph can sometimes cross an asymptote. The whole idea with an asymptote is that, once you have this boundary, the curve is going to be approaching the boundary, but it's not all of a sudden going to cross the boundary and then, kind of dip below and come back, or, at some random spot. Or if that did happen, we would know those points from our work in part C here. Okay. So now the way to check if a graph crosses a horizontal asymptote would be to set the function and the asymptote equal to each other and then solve for x. Any solutions to that equation would mean that there's intersection points on the graph. Okay, so I've got this set up here. I'm setting the function equal to the asymptote and solving for x. You're going to multiply both sides by x squared minus 4 to get rid of the fractional form on the left. Okay, if you subtract x squared from both sides, then that leaves you with -1 equal -4. And of course, that's not true. -1 does not equal -4, right? But x was eliminated completely in this calculation, and you got something that was not true. That means that this equation has no solutions to it. Okay, now as far as any intersection points, then there would be none of those to worry about. So at no point will the graph ever cross or intersect the horizontal asymptote there. Okay, part D. Determine the intercepts for f and then sketch the graph. Plot additional points if it's necessary. Okay, so I've got my work for getting the x and y intercepts shown to the right. How we calculate an x-intercept is we need to let y be 0 and solve for x. How we calculate a y-intercept is we need to let x be 0 and solve for y. So whatever kind of intercept you're wanting to find, let the other guy be 0 and solve for that variable. Okay, so I want to find an x-intercept. I've got to let y be 0 and solve for x. Now, y and f of x mean the same thing, right? So when I say let y be 0, I actually mean let the function be 0 and solve for x. So I'm doing that. Multiply both sides by x squared minus 4. That'll clear out the fractional form on the left. X squared minus 1 equals 0 means that x squared equal 1. If you take the square root of both sides, then x would be plus or minus 1. Don't forget about the plus or minus there. Okay, so we're going to have two x-intercepts at 1, 0 and -1, 0. To get the y-intercept, I need to let x be 0 and solve for y. Well, x being 0 means that I would just plug 0 into the function. And when I do that, I'm going to have -1 divided by -4 is 1/4. Okay, so 0, 1/4 would be where the curve crosses the y-axis. Now, after doing all that, I only know 3 points that would be on the graph here, these 3 intercepts, and I've got the asymptotes. I've got 2 vertical asymptotes here at x equal 2 and then x equal -2. Through division, we found that there's a horizontal asymptote at y equal 1. And like I said, after doing all this work, I only know 3 points on the graph. Okay, that's not a whole lot. Of course, I do know some other, key information like the asymptotes, like I said, but I'd want to plot some additional points just to have, the graph complete. So I've got a table of numbers set up to the right of this here, and I'm just going to gather up a few more points. Now, in the middle section, I've got these 3 points, the intercepts, already plotted. Of course, the graph has to flow with the asymptotes. So the fact that I've got these 2 vertical asymptotes and this horizontal asymptote means that I think that in this middle section here, the graph is going to be coming up the left vertical asymptote. It'll be on the right side of that, though. Pulling away from that slightly, it's going to come up, reach a peak, and then approach the right vertical asymptote, but from the left side of it. Okay. So I need to get the left section and the right section finished off here in this picture. That's where the table comes into play. If I let x be -3, and I plug that in here, -3 squared is 9, -1 is 8, and we're dividing by 5, so I'm getting 8/5 as my output. Okay, so here's -3 8/5. Now that single point being located where it's at, and the fact that I've got a horizontal asymptote here at y equal 1 and a vertical asymptote right here at x equal -2 means that I think I know the story of what's happening on the left-hand side here. Of course, the graph has to flow with the asymptotes, right? So I think that this curve is going to be coming along above the horizontal asymptote, be rising slightly. It's going to pass through that point that I just plotted, and then approach the vertical asymptote from the left side, but it's never going to get there. Okay. Now, knowing that point is located, where it's at above the horizontal asymptote, means that if I'm on the left side of the vertical asymptote here, I'm going to be above the horizontal asymptote, or I'm going to be in the upper left-hand region of this picture. Okay. If I were to let x be 3, just to get the other section figured out here, plug in 3. We'll have the same output as when you were using -3, right? Since 3 squared is 9, 9 minus 1 is 8, 9 minus 4 is 5, right? So you're going to have 8/5 coming out of that function there when x is 3, and here's the point 3 8/5. Now that point being located where it's at, along with the boundaries that I've got there, pretty much tells me the rest of the graph here. Again, the graph has to flow with the boundaries. So I think the curve is going to be coming down the right vertical asymptote, to be on the right side of it. Going to pass through that point and then approach the horizontal asymptote, but it's never going to get there. Okay, now I know I'm not going to have any graph in the lower right-hand section, right, because it's going to be a function, and I've already got a curve drawn in the upper right-hand region. I'm not going to have anything below that, otherwise it's going to fail the vertical line test. I also know that I'm not going to cross the horizontal asymptote, right? My work here in part C was, although I wrote none, this is still useful information to me. At no point will this graph cross or touch the horizontal asymptote. Okay, it's going to approach it, but it's never going to get there, type deal. Also, this graph is symmetric to the y-axis. Good observation, but we didn't use it here in any of these steps, but still a good observation. And that's a good observation because ideally it would reduce the amount of point plotting that I would need, right? If I know that I've got this point on the left side of the y-axis, I know that by symmetry I'm going to have the same point directly on the other side. Okay, the graph is symmetric. That can save some time. All right, at this point, we are now done with the algebra part of what I wanted to do and review. Of course, as I mentioned at the beginning of the notes, algebra and trig are two very big fields in math, and we're going to be doing lots and lots of algebra and trig along the way. At this point, once we get into the calculus, we're gonna need our background from algebra to be there, and we'll just review things as we need them, on an as-needed type basis thing. So in the next video, I'm going to get started into the trig review.